So now I want to combine different studies. So what I want to do is that, so you have, normally you start with a uniform stress and then you let it relax, your geometry reaches its steady state, and after then you calculate the eigenmodes. That's the idea. And then through that I'll also teach you like how to basically calculate stuff like Q's, effective mass, and stuff like double clamped. Simplest case that I can think of, I told you, if you work with a cantilever, even if you start with some pre-stress, you cannot hold that pre-stress because there's nothing to hold it mechanically. You would just, if you start, it's like a spring that is basically pulled, and then you cut it and it just shrink. So a cantilever cannot withhold the stress, but a doubly clamped beam can. If you have two beams connected to these pads are pulling it. They don't let it shrink. Okay, so very quickly, let's build this geometry. I mean, this something that I didn't ask in my modules and my files, and cannot access the drive. So then I assume like all of you have. So now you can go to the fifth example. By the way, we didn't go to details of 3 and 4, so I invite you to go through it. I just quickly flashed out. So it's a doubly clamped beam. Again, in the interest of time, it's a simple geometry. We have drawn it. It's just a rectangle. It's a block. So now the difference is that what we want to do is two studies after each other. So we want to use first a stationary solver to calculate the stress profile, and then use it as an initial value, feed it to the eigenmode solver. So fortunately these days, if you go again in new versions of COMSOL, we can start with your model. Model wizard. We go to this structural mechanics, and then we saw this eigenmode frequency. So this pre-stress analysis eigen frequency. So this is nothing but just combining two studies. You can do it manually. You can start with stationary and add the eigenmode. So actually we used to do this in old days, but they implemented in COMSOL. So now you would see, let me just close this so my computer doesn't crash again. What you see is that everything is pretty much similar. So the same geometry, stress 900 megapascal I put. We can put the 1 gigapascal, that's the order of magnitude. This we don't care. Geometry is just one rectangle. We draw it together. We're going to assign the material, but the only difference here is that you can see in the study number 1 there are two study steps. The first is stationary, the second is eigenmode. As I said, you can, if you do go with this pre-stress analysis eigenmode, it would just automatically put 2. You can start with pre-stress and add the other one. And then if you want to do more complicated stuff, you can. That's the logic. You can see. This is how we do multiple steps. So we just stack them, and then so there are settings that you can just feed the beginning, like basically the values of this as initial value for the second one. So to do this physics, the only thing we need to do is just basically assign the material. We have silicon nitride assigned, all good. The silicon is we can delete it, doesn't matter. So silicon nitride is assigned, and the only thing we need to do is just boundary condition. Boundary condition, two things. We need to put the initial stress as we did in the previous example. So right click on linear elastic material, and then you have this initial stress and a strain. So exactly same idea. Again, we put this initial stress for XX and YY component. Again, I told you in Z components it's impossible to have stress in reality. So that's good. Then we put a boundary condition. The difference between this, this cantilever and this case is that now we need to basically fix two ends of it. So it's doubly clamped. So this surface and the other one, both of them needs to be selected for this, fixed boundary condition. I'm going a little bit fast here because I've shown you this, so there's nothing complicated. If you cannot follow, just ask me. Okay. Well, So our study is complete. Mesh, again, nothing complicated for the moment, like just physical, like basically automatic mesh, and we go for the study. So what is the study? One stationary. Here, this is very important to click on this, basically include geometrical nonlinearities. The same for eigenmode solver. And then we choose to simulate the first 6 around 0 DC. Okay. So let's simulate that, and then what I want to show you is mostly on how to extract some results. So I just hit the simulation. You do the same thing. So while it's so now if you look, there are two solvers. First would be the nonlinear solver. It reached. So if you look at the convergence plots, guys, here. So the one convergence plot will be for nonlinear solver. It's reached. Then it starts the convergence on the second, which is the eigenmode solver. And it uses the values for calculated for first as the initial value for the second study. Okay. So Mohammad in next talk will teach you how to modify the physics tree in different study steps. In his example. Okay. So now we go to the results, and then not surprisingly, obviously we see this eigenmode and higher order modes. Again, as usual, so in plane, second order modes, etc., etc. Again, I told you a lot of times already. The first thing we need to do is, so we know so if you calculate for this given geometry, the eigenmode is 2.3.9 megahertz, and so we know the basically analytical solution for a stress of 900 megapascal. If you insert it in this equation, you would get 2.69, and then tada, there is a difference. So something is up. This is a huge difference. Previously you saw that there is like 1% error is okay, but it is not 1% error. So why is that? And then if you try to fit that, you would show that the value you need to put to get this number, effective stress, is 700 megapascal. So 700 megapascal is the effective stress, but what happened? What the hell happened? So see whether really the stress is 700 megapascal after you relax or not. Because remember, it is like basically in one dimension it's bound by two paths. In the other dimension it can shrink. Is nothing there to hold it. So part of that stress will relax in the other dimension. Well, for doing that, you can just come to the same simulation and just disable the eigenmode solver, because just automatically just throws away the results of the first one. So just disable the eigenmode solver and then just delete this basically basically just say delete configurations, this solver configuration, because it's in the memory that it needs to do the eigenmode solver. Just delete that memory. We come back to it and just hit the study of just now it becomes one step of a stationary. Simple. We just disable the eigenmode solver. So it converges really fast, no surprise. So now we can go and basically see how much the stress is in this film. Okay, so you can see it's color coded, but it's maybe difficult to read like how much it is exactly. So one thing that is, I want to tell you like how to extract data out of this simulation, not just by color code. So if you want to, for example, like basically see a cross section or a line or a point, how do you do that? So if you want to like extract the data of a line or a point, you can just come to this data set and then right click on it. Under results, right click on it, and then here you can see different things. You can have cut plane. You can just cut a plane through your object and then see in 2D. You can cut a line through it. You can choose a point, cut points, surfaces, edges. So what we want to do is just cut a line through the middle of this beam and then show how just see how the stress changes. So you can have cut line 3D, okay. And then here is like you just you define a line by just coordinates of two ends of the line. So we just put the values of the beam. So like basically minus L of beam half is the other side, y is 0 is the center, and z would be the thickness of SIN divided by 2. Okay, and then the positive. So, if you follow me, this is the coordinates of two ends and line at the center of this this basically slab that we have. Huh? So to make sure that you have done a proper job, you can plot this line that you draw. If you just click on plot, it just draws you the line that you just draw, and you can just make sure that this is, yeah, indeed it's a line at the center of the beam. It's okay. Huh? So now we can basically plot or extract, or as we wish, the values of the stress on this line. Let's do it. So what for that we need to have a, so you can have different plots, 3D plots, 2D surface color coding plot, and 1D. If you have a line, you can use a 1D plot. So y-axis would be stress, x would be the basically coordinates. Huh? So you can have 1D group plot. And there, first of all, you need to tell him which data set to choose from. You just choose your cut line. That's the data set you want to draw. And then if you right click on it, you would have line graphs, for example. You have different options, point graphs, global. We will learn this stuff as we go forward. But just, the easiest one is just one line graph. So now we just need to know, we just need to tell him what is the x and y like basically axis of this one. So y as default is now displacement. So let's start with x. X would be the x coordinates, geometrical coordinates. So if you go to x, go to your geometry and then coordinates, material or spatial, you can choose x. Okay, so now just to just give you a feeling, y-axis is solid displacement, it's a total displacement. So if you hit the plot, let me see which. Oh yeah. So there is no displacement actually. So you can see displacement is in the order of angstrom. Because it's a stationary solver, we don't need to have it. So if you change the y-axis, actually go here and then go to solid mechanics, then go to a stress Gaussian point, and then a stress I told you is a tensor, but you can get a scalar value out of this tensor. I won't have time to go through it, but it's famous and it's a very famous basically type of stress. Von Mises stress. It's a scalar that you extract from this tensor. Just read it in Wikipedia. It's like 2 lines of basically equation. So it's a kind of a, and then if you plot such a thing, it would be interesting. Like just look at this. We started with a 900 megapascal, and then now the stress at the center of the beam, how much is it? 700 megapascal. So stress has been relaxed a little bit from 900 to 700, and it makes sense. Why? Because from an analytical solution, we saw that the stress of 700 megapascal will give this number. Okay, so again, you don't have a simulation software doesn't have a brain. You do. So know what you're doing. Okay. So if you have an initial uniform stress, it won't stay uniform. It would relax in the area that it needs to relax. Okay, if you don't pull it, if you don't have any object to keep it there, it's a spring. I told you, any material is like a spring. And initial stress is like pulling it, and if you have nothing to hold it, it will, like any spring, will shrink or expand. Okay, so and as my last basically slide of this, I want to just introduce how we calculate the effective mass. So what is the effective mass in optomechanics? effective mass in optomechanics is practically you just calculate the kinetic energy of the mechanical oscillator and then you normalize it to the amplitude of 1 point. So it's a little bit like it's ambiguous definition because depends. So how do you calculate this integral? Calculate some values. For example, kinetic energy in this mechanical oscillator. And if you want to do that, you just come to this derived value, just right click on it, and then you have different functions here. So you can see you have average, you have integration, you have maximum, minimum, etc. So to calculate the kinetic energy, you need to integrate the kinetic energy over the entire object. Let's just do that. So integration, I'm going a little bit fast, but let me just I want to show you how to integrate in mechanics, and then I will give the floor to Mohammad. So for example, if you want to integrate something, first of all, you can choose where to integrate. Obviously, we have one domain here. We choose that domain, and then now you calculate which expression to integrate. So you can choose what to integrate over this volume. There are different things to do, and here to calculate the effective mass, if you go to solid mechanics, again, you can choose the value with this, green red arrow, and then solid mechanics. From the displacement vectors that it calculates, it also can calculate, I told you before, acceleration, displacement. We saw the stress, but also energy and power. So energy and power, and then if you see, you can see elastic energy, stored energy in density, WH. This is the normally one is this energy stored in this kinetic, one is the energy stored in the thing. And if you want to calculate, for example, this is the kinetic energy, and if you calculate that, you will integrate it, and obviously we are doing a stationary solver, so you need to go to the Argand solver to see the energy of different modes. Okay, so if I go back and then enable this Argand mode solver and clear my thing, Mohammad, you can come. I mean, I'm almost done. So if you go to Argand mode solver and then calculate that energy, it can calculate the kinetic energy of different modes. And then you can, from that point cut, you can take the displacements of any point you want and calculate the effective mass respect to that point. Normalize it to the amplitude of that point. Is that clear? So that's how we calculate the effective mass, normally using the integration. And the last thing I want to tell you, there was a question how we calculate the losses. And losses, we know that the Q dilution factor, I mean, this is a topic of its own. You can calculate the losses by, if you know the intrinsic non-stress Q, times this so-called stress dilution factor. And this stress dilution factor is the ratio of the energy stored in the elongation or kinetic energy divided by energy stored in only a strain. Why is that? Again, not a topic of this workshop. If you want, it's a topic of its own. But that's how kinetic energy and stress energy, and calculating the division of these two will give you the stress dilution factor. And if you know the intrinsic Q, you can do it. There is another bonus way to do it. You can use the imaginary parts of Young's modulus, but I will not cover it until we get to this point. So what I want you guys today in exercise session, actually use the knowledge we gained today. So we have a stress film, we have these fillets, calculate the stress profile, calculate the Argand modes from it, and then via this integration calculate the Q, see if this effect of this, basically fillets, how does it affect the Q? Does it increase it or reduce it? We are like basically enable, now we can simulate such a thing. But I will actually stop here. Okay, so you can.
Do we need this?
Yeah. And then I will come back after this talk to see how we can use this periodic basically structure in practice. Okay, so floor is yours.
Okay, thanks. Okay. So already there. Hello? I don't see much difference with this, but I hate these things. Okay. So I just want to make sure that I'm loud and clear. People in the back. Okay. So what I'm about to do today in this session, actually I wanted to help you guys through drawing your own geometry and getting it to work, but since we might be a little off time, I have put the geometry in the Google Drive, and I will guide you through how to download it and get it into your COMSOL. So let's do that, and then I will just tell you about different parts that what's the idea behind, so you can do it of course for yourself once. So I'm going to do a little bit of exercise here just for myself. This is the Google Drive that I hope everybody has access to. I just uploaded the model that I wanted to that I wanted us to build together, but just refresh it once because it might not be refreshed. You can go to software and COMSOL, and then there should be a 1D phononic crystal. All right. So here you need 3 files. The first one is the COMSOL model. This one. Here you have the MATLAB code that I will tell you what it will do, and then you have these parameters of the model, which I already put in because I was planning that we build this all together. So just if you download the file here, okay. Just give it a time to download because it might be a bit heavy. Also the MATLAB code. The parameters now you don't need because they're already included in the model. So so while it's downloading, I'm just going to show you a very brief introduction of what I want to do. And then in the presentation, I already included all the steps. So in such a case that you want to go back and check it once more yourself in the future, you will have reference. So just very quick, like in 2 minutes, I don't want to educate you guys. I'm sure that you all know the concept better than me. So just a quick review for myself. First of all, sorry, because I was a bit rushed into the presentation, I didn't introduce myself. I'm Mohammad Bereyhi from EPFL. I'm a grad student in the group of Tobias Kippenberg, and I will be presenting for you a very simple idea of periodic structures in mechanical structures. So periodic structures, they can be 1D, 2D, 3D. The basic idea is to have some different materials appearing one after the other. Of course, there are some difficulties in making your structures this way. You will have to deal with several fabrication issues, but this is a price you pay, and you will gain something out of it. So, because I'm much into the nature, I don't want to talk about this, but you can find periodic structures in the nature everywhere. So that way they manipulate light. This one is also the first derivation of mechanical bandgaps. So this is an old paper by Lord Rayleigh. This is somehow the first forbidden bandgap in mechanical structures. And actually this one is a bit funny. I always like to mention this. Does this work? Okay. Actually, this is 2 papers in one, something that people don't do these days. So it's actually 2 papers in one because he was a lord. He didn't have time to write 2 papers, probably. So how do periodic structures work? So the idea is very basic. You have your a structure and there is a periodicity in your structure is appearing on and on again in the same way. So no matter you're dealing with Maxwell equations, Helmholtz equation for electromagnetic waves, or you want to see the mode shape of a vibrational mechanical mode, the basic idea is this, is that your structure is the same if you move by the vector A, which is your periodicity vector. And the idea is when you have a differential equation and your coefficients are periodic in this manner, your solution will also be periodic. So your solution here would be similar as your solution here. So there is a periodicity in your solution. So there is the waveform is the same, and there is just a phase shift. So what we can do with this, we can generate a band gap. This is a dispersion of a simple structure, a doubly clamped beam. You see different modes. This is a wave vector, the normalized wave vector, and these are frequencies, for example. So you see this mode is the dispersion looks like this. So with having periodic structures, what you will gain, as I described, so you're going through several difficulties in make them. You will have forbidden regions for wave to propagate, which are called as band gaps. For example, in this dispersion, you see the band gaps are here, so here the modes cannot, there is no mode propagating here. And of course, maybe, for example, these modes are from different mode families, in and out plane. I'm not going to describe you this because this will take time and I don't have it. So, and also a very simple picture of physical picture of how band gap works. So what do I mean by the band gap? If I have an input wave, so it will be reflected by the first boundary, also by the second one, on and on again. So for some frequencies, which I'll call them the band gap frequencies, these will have a destructive interference and I will see nothing. So this mode cannot propagate. Just give you a very hand-wavy idea of what a band gap is. So how we are going to use that, there are several applications for this. For example, here I have put 4 papers in the fields of optomechanics here. For example, here you see in the middle they have a photonic crystal defect cavity, and here you see they have some phononic crystals that is shielding the vibrations of the structure. And also, for example, here they have a membrane in the middle, and surrounding you can see there are periodic structures, so the mechanical waves, there's a band gap for it to shield the mode here. And also here, for example, the idea of optomechanical crystals, they also work with the band gap, something that Professor Marquardt already explained to us in the Erlangen workshop if you participated in. And also this work from our group, which we have a doubly clamped beam here with a micro disc, and we use these structures, these periodic structures called phononic crystals, in order to shield the radiation modes. And here what I'm about to show you is how to simulate the phononic band gap of such a structure and see what are the regions that you have no mode propagating, so you can shield your structure. Here I have put all the steps, so you can go back and check it if you forget some of the steps. But now let's get to the software. All right. So I'm going to close this. So I hope you already, all of you have your models downloaded. So I just take these 2 files. Here, make a folder for myself. Call it Phononic Crystal 1D. All right. So if you open the COMSOL model, everybody just want to make sure that everybody can open the COMSOL model. Yes. Have you tried refreshing it once? Okay, is it fine? All right. So in order for you to see it better, I put this magnifier here. And the geometry I already modeled it here, but I just want to go through the steps of if I wanted to start from scratch, what would I do? So just a quick, okay, that was in the simulation, but I forget to show you. So this is the structure that I want to simulate. This is what was what we called them phononic crystals, and so here we have a large section of the beam and a small section, a large section, and it happens all around again. So how you want to formulate the geometry is up to you. What I defined here is the ratio of the L small to the L of the unit cell. I defined it as the unit cell ratio, and so the large part would be this expression. So just for your future reference, if you go back and you want to see, don't get confused with this ratio. Okay, let's magnify it. All right, so I have defined several parameters here. For example, this one, the width of the beam for the large section. This is the L of the unit cell, the width of the beam in the small section, the ratio of the thin part to the thick part, and also the thickness of the film. And here I have two parameters. This one is the normalized k vector, the vector, the propagating vector, the wave vector that I normalized it to p over the length of the unit cell. So this is the Bloch vector, this is the k, but if I want to sweep this, it's more convenient to sweep something between 0 and 1 and then multiply it by your normalization factor. So first I define my parameters and go to the geometry. So the way I recommend you to do it, if your structure has a symmetry in some way, and if you can imagine your structure in 2D, I usually add a work plane here by just simply right clicking on the geometry. So here you have your work plane. If I get it back to this view, so my work plane has a plane geometry. So the plane geometry is a 2D models, and you just extrude it to get the third dimension. And in the plane geometry, what do I have? I have the large section. If I build the selected part, sorry, I named them the opposite way. So it's the small section here, and for the other one, it's this one. And there's a trick you can always do. If your structure has a symmetry, I put a mirror in here, as you can see, and then I just mirror my structure. This will, but just to be clear, all your dimensions should be half, and so you multiply it by 2, and then you form a union in order to have your structure unified, and then you have your 2D model, and then you just simply extrude it by the thickness parameter that you already defined. So this way you will have your structure ready. And the next step is to, if you run it now, COMSOL will give you, will ask you, okay, what's the material? So this is a material that I use. It's silicon nitride. Let me magnify it a bit. So here I use silicon nitride for the whole structure. And for example, you can see material properties like the density, Young's modulus, or Poisson ratio. And just a quick note, if you want to if you want to select a material from the library of the COMSOL, which is here, if you're doing mechanical simulations, probably if you have some materials that have both optical and mechanical properties, you will have two or even more options, like from optical or MEMS. Try to go with the mechanical one, because otherwise that model will not have the mechanical parameters like Young modulus, but that would the emphasis of the model would be on optical parameters. So here I use silicon nitride, which is a high stress material. Amir already introduced you to the effect of relaxing the stress, and first I want to do a study without stress relaxing, generating a bandgap, and then I will show you, okay, if you put the effect of stress, that would be a different. So once more, simulation softwares do not have brain. Okay. So for solid mechanics to study, so now my material is defined. What are the studies that I want to make? So I have a linear elastic material. My material is free, and there are some initial values and a periodic condition. So first of all, I don't want to include any stress, and then just because my structure is like this, and if you want to zoom in, just keep your scrolling button and just roll your mouse. Then this will move it, because this can be handy. And if you have some weird view, you want to reset it, just click on this one. This one will reset your zoom into your view, okay? So my structure is periodic, so this face and also this face will connect to something similar. So I want to add a periodic boundary condition. So if you come to connections, periodic boundary conditions, I already put it here. You will have this. You have several choices here. As I described, the Fluke theorem for the periodic boundary conditions. Here I put the type of periodicity to the Fluke, and the k vector of the Fluke periodicity is the direction of my periodicity, which, for example, here it's in x direction. You see here is x, and the periodicity will be in x direction, and my periodicity vector was kx. In the parameter we already introduced it, and then so the boundary conditions of my structure seem to be fine. So let's move to the meshing. So the trick here, the point is, since you have two faces that are similar, this face and also this face, you want everything to be similar for these two faces. So one way would be to add a free triangular mesh, and then first mesh your one of the boundary surfaces. Just mesh the surface, which I already did. You can also define a size for it. You can change it into fine, extra fine, whatever you like. And just one thing, if you increase your mesh to a very extreme value, if your model does not converge or does not give you a correct answer, increasing the mesh will not help. So increasing the mesh always does not mean that you get better and better result. So after meshing this surface, one thing to do is to copy the space. So here I already copied face 1 into face 16, which is the other one. So I want everything to be similar for these two faces. And then I put a free tetrahedral meshing for the overall remaining parts. Here you can see for the all remaining. So the structure is already meshed. And then let's get to the study. So what we want to do, we have a structure and we want to see the eigenfrequencies. If I just click on eigenfrequency, you can see that I have the desired number of eigenfrequencies to 20. So for each k vector, it solves for 20 mode. It just solves for 20 mode, and it searches around 0. And as always, I want to include the geometry nonlinearities because sometimes due to the sharp edges, some effects may happen. And then if I click study here, it's going to be very quick. So I will just solve for the modes of this structure with the boundary conditions being the periodic boundary condition, and you'll see different modes of this structure. And for example, here you see the convergence plot, so it's going okay, it's not oscillating and not converging. So, oh, actually I'm doing a sweep, so sorry. Okay. All right, so since I have this model, there's something I forgot, my bad. So here in this study, if I just disable this parametric sweep and I just solve the model, it just solves for the eigenfrequencies. But this is what you already did for a doubly clamped beam, and the main of this session is to show you how to simulate the band gaps. So the idea is to sweep your k vector and solve for the eigenfrequencies in each k vector, and then plot the dispersion to see how the modes look like. So this is what I did here for you in the parametric sweep. You can just simply add it by right-clicking and adding a parametric sweep, and it sweeps a certain parameter that you would like. For example, you have a waveguide, you want to see the dispersion for different width, and so this is something useful to know. So here you can add your parameter. Here I put the normalized k vector, and it's arranged from 0 to 1 with steps of 20. So it will solve for each k vector the eigenfrequencies, and then it will give me the result. So if I click on study, this will give me the eigenfrequencies for each k vector for this structure. And keep in mind that the silicon nitride was a high stress material, but I did not do anything regarding the stress profile and the stress release. So here we're doing actually a wrong simulation, but I want to show you that if you simulate it like this, and then if you add the effective stress, your band gap actually is different. So it's about to finish. So here you see that it's good and converging, and I didn't do anything about that. It's automatic Newton convergence. So we'll go for the 20 k vectors that it's supposed to. Okay, and right now in the results section, you will have the mode shape, and then, for example, in the eigenfrequency, you can see different modes. This is not something new. You already saw it for a doubly clamped beam. For example, for different modes, you will see how it looks like. This one is weird. Okay, this one's nice. All right, and so what we are interested in is the eigenfrequencies versus the k vectors. So what we do, we just right-click here, add a 1D plot, which I already did, this one. And it's a global type, so you can access all the variables in your model. For the y, here you can use for the solver the frequency, which I already did here for you. The frequency is your y-axis, and your x-axis is the expression is kn kx normal, which we swept. And here you can access it, for example, in global definition, parameters, and kxn. All right? So if you plot this, this will be your band diagram, but if you show this to anyone, they will be confused and say, okay, tell me what's going on here. So this is how COMSOL solves your structure. It just sweeps k vector and then solves for eigenfrequency. So it has no idea what you want to do. So now the idea is to export this data, take it to the MATLAB, and try to plot the modes to see the dispersion of different modes. And the approach there is to sort your, I'm just going to give you a quick idea of what the code does. You just sort your eigenfrequencies, and then you try to connect each dot to the other. For example, this one, you have several options to connect, all right? And then you see which line gives you the minimum derivative, so it shows somehow the continuity of your dispersion. So for that, here you have the export. You can just add the export from your plot. So you want to export all the data here in the plot section. You're using the data from 1D, and for example, here I'm exporting it in my folder as eigenfrequency kx no stress. If I export it, okay, it's already there. I will get okay, sorry. I wanted to do it from scratch, like you. In desktop, in my folder for Phononic Crystal, if I save it, all right, it should be there. It's not. Save. Okay, it should be there now. Okay, here's your text file. Here you see that this is how COMSOL will give you the results. So for k vector 0, these are all the eigenfrequencies. For this k vector, these are all your eigenfrequencies. So let's use the MATLAB code here. I hope everybody has MATLAB installed. Otherwise, just you can try it later on. I think that was the name of the file. All right. So if you run it, it will connect the dots in a reasonable manner. And for example, here you can see that here no mode can propagate. Also here, so this is the band structure of what you simulated. All right. Everybody with me? Okay.
Can you say it again? How we link this plot to the vertical lines?
So the idea is, for example, for each k vector, you have different. You have just the eigenfrequencies sorted here, and you don't know what is the next one. So if you just plot the, for example, your text file, if you just get it, and for example, you have this these two columns, and then you have it for different case, and if you plot it, you will have the same thing, but there will be all dots, and you cannot, for example, calculate the derivative of everything. So it's like this. There is no magic. So what I do here is I want to relate this point, for example, to its neighboring, not, for example, to this one here. And the way I do it, I get a point. I measure I calculate the derivative with respect to the neighboring point of each one. So it will give me different slopes. And I will choose the minimum slope, which makes more sense. So then, you already saw that silicon nitride is a high-stress material, and the stress inside plays an important role because it will affect your the speed of sound, your Q factor, and everything. So what we want to do, we want to modify our study here, our model, in order to make it more sense. In order to have more realistic simulation. So what I add here, I will go to study steps. Yeah, sure.
Yeah, maybe I missed something.
All right.
So you have a plot here,
Mm-hmm.
more or less uniformly distributed frequency.
Yeah.
When you plot it in MATLAB,
No, this is just the difference of the points. I mean, this plot is not a nice plot. The scaling, it's a bit misleading. If you take all the data and you just plot in the MATLAB, the spacings would make more sense. This is just a bit misleading. Sure.
You take the difference in the second derivative and then the minimum of the second.
The first derivative, no.
But then in your plot, it should be different, because there are some points where they cross,
Exactly.
and then it would take another one.
No. Here's the thing is, like, you have, when you cross, you have a bunch of options.
Yeah.
And then
Yeah.
you choose the one. So you take the slope of with the point previous. Like,
So it's the difference of the slopes, not just one slope. The previous slope and the next slope. Right. That's the second derivative in that case, sure. Yeah, of course. So if I want to include the stress, here you can follow me in this step because it's not included. So you add a steady step, a stationary, and here you can solve the stationary solution of your structure. So you, as Amir described, you set an initial stress and then you let it relax. So here I place it first because I first want the stress to be released, relaxed. I want to solve the stationary solution of my structure and then go to the eigenfrequency solver. So here I need to have some boundary conditions for this study that I added. So what I do here, I come to solid mechanics, and in the linear elastic material, you can add an initial stress and strain. So here we can add the initial stress. Already Amir explained it to you. So here for my stress matrix, I'll write, for example, stress initial for X, initial for Y, and for Z you already know that it relaxes in this direction. You don't need to, because it's not bounded in Z direction. This is not defined, so what you can do, you can just come back in your global definitions, parameters, and you can define your introduced variable. I, for example, here set it as 900 megapascal. Okay. This last one is not bracket, yeah. All right. So here I come back, I see the initial, so the initial stress in X and Y is defined, and you see there is no. So there is one there is one more boundary condition that you need to add, which is a fixed boundary condition. So you want your ends to be fixed, and then release your structure, because if it's all free, there is no point in relaxing. Sure.
Sorry, just a small question with the order of the study steps.
Okay.
Parametric sweep, does it matter where you put it?
No, it just solves it for every k vector. So the parametric sweep solves these two for different parameters. So it doesn't matter where you put it.
You theory say first stationary and then a parametric sweep for step.
Yes, yeah. But
It seems like a loop. If you write it in MATLAB, it's like a for everything that's happening.
yeah, because you're changing this parameter of k vector each time.
Is it also possible to add two parametric sweeps?
Yeah. You can add two parametric sweeps, for example, here for different variables, and but then it will solve for all the combination. You can add it, for example, if this one is n times m, so you have a matrix.
Like a David for.
Yep.
Question on the stress release.
Mm-hmm.
On the boundary conditions that you're about to impose on the system. Doesn't that kind of, if you now fix one end of the boundary system, doesn't
Mm-hmm.
that reduce the number of your solutions?
Sorry? Okay, can you repeat it again?
Doesn't, if you now fix one boundary
Okay. This I'll come to it because it's a bit different from the periodic boundary conditions that you put. Because in the periodic boundary condition, you're saying that this is happening again and again, and now you're fixing it. These two are a bit crossing. Actually, this is a good point, and if you just run your simulation like this, here, for example, I add in fixed constraints, I add, for example, that this surface is fixed, and this surface is also fixed, all right? So what Simon just mentioned, there is something not making much sense. So the point is, when you want to solve your stationary solution, you have to put your boundaries fixed and then solve for the release structure. But when your stress is relaxed and you have the profile, then you don't want these two to be fixed. You want this to be the fluke condition. So you want this to appear again. So here I'm going to show you how you do this. Because in the first, when you want to make your model from blank, if you want to make a blank model, there is an option like pre-stressed eigenfrequency. But here I just use the eigenfrequency. I'm just modifying it to something which is more true, I would say. So here in the stationary solution, you can, here I include geometry nonlinearity, because here is a bit important. Let me magnify it a bit. So here you can modify the physics tree of your solution, of this solution. So here, as you noticed, when I'm solving for the stationary study, I don't want the periodic boundary condition. So you can just disable it. But in the second one, which is the eigenfrequency solver, you can again modify the physics tree. You don't want them to be fixed. You want them to be periodic. So here you disable this one. Everybody on the same page? Can I just get a nod? All right.
Okay, let me just add one thing to here. This is the same idea if you want to do studies and also change yourself in the middle. So you can, this is an example of changing the physics tree in between the studies. You can do more complicated stuff. Add physics, remove physics, remove geometry, add geometry. This give you a taste of how it's being done.
So now I have my studies all sorted up and all with the correct boundary conditions. And then when you compute your result here, I will just show you how it looks like. So here I have for you put all the steps, including drawing the geometry. So if you want to go back again, do it once yourself. This can be a reference for you. I mean, if you forget some steps. And these are the two results that you will get. This one is when the stress is not relaxed. this one. And for example, it's a bit hard to see the difference, but for example here for these two modes, if you follow me here, these two are not crossing in this sort of wrong simulation without the stress. But here if you apply the correct form, for example, here you see that these two are crossing. For example, the dispersion of this reddish line, it's also different. It's not coming down, and it's now here almost flat. So, and these two graphs you can also get with the derivative or the second derivative approach. And the code might not be the best case because I wrote it very quick, but if you had any questions, we can discuss it in the exercise session, because there I think we prepared a model on a phononic shield for vibrational breathing modes of a microdisc. So you will have a microdisc, see how the modes can radiate into the substrate, and then you put phononic shield in order to shield your structure and generate a band gap. So with this being said, I think I'm all done, but Nick had a question.
Yeah, I was just wondering why you use fixed boundary conditions and not rolling.
Not what?
Rolling boundary conditions, because now you hold your beam at a fixed.
Yeah, because my beam is doubly clamped from two sides, and I want to see if it's clamped from two sides, how the stress will relax. Because that's the case, your beam is clamped from two sides.
But it gets thinner, right? Also on the sides.
It can be, yeah. Yes, true, it can be, but here I'm just simulating one unit cell. That's true what you're saying. You can simulate your whole beam. You can draw it, and then you can see that the clamps will shrink. If you, for example, have, I don't have the model now, but I think Amir will show it. You then put your pads to be fixed, and you can see actually your clamps will be shrinked. So yeah, you're right.
What you said is correct. Actually, we are trying to model what's happening in reality. We
Yeah.
need to do some approximation, because
Mhm.
you cannot do stress release with fluke boundary condition. Just doesn't work. Doesn't make any sense. Huh? So we need to use a fixed boundary condition. But I mean, that's what you said is true. In reality, these 2 points are not really fixed. Fixed is an approximation of what. So I'm assuming it doesn't shrink very much in this direction. It is not so bad of an approximation. But that's the closest I can find to reality. They can do more complicated stuff if I want, but it just adds more complexity.
So
Again, it's the same question.
if there is any question.
This software is too. You're the ones you need to know what you're doing. Question.
Sure.
So what was again the difference between these two plots?
Well, in the left one, in my model, I just draw my model with the high stress material, and I did not let the stress relax. I just solved it. I mean, just drawing it and solve it. But in this one, I first did a stationary solution, so I fixed the boundary conditions at the end. I just fixed it, let the stress relax, see the stress profile, and then use this stress profile to solve the eigenmodes. And this happened on and on again for different k vectors, creating this. And for example, you see these modes are crossing, but here they're not. So there is a difference in the dispersion of the modes in these two cases. Okay, thanks.
Okay. So actually, the last part of my talk for this morning, I invite you to actually open this. Sorry. Just let me see. Okay, so if you go to this basically folder, Google Drive folder, this time the geometries that I want to use for this simulation is sort of complex, so we don't have really time to do it. But so the topic of like this, last 30 minutes of my time is basically the applications of. We can use phononic crystal for different stuff. We can use it for like mode shape engineering. This is a new trend. But as Mohammad told you, you can use it as a shield.